So let's just say a few words about L Acoustics. So we were founded in the middle of the 80s, and we're a French company, but so most of the manufacturing and R&D is based around Paris in France. We also have sites in Germany that do the amps manufacturing. And we also have a small R&D office here in London where we do all the spatial audio business. So what we do best is big speakers, very big speakers. So if you've been to a concert, you've likely seen this kind of deployments, which are called line sources, which were pioneered by Acoustics in 1992. And that really changed the way we do live sound, bringing the speaker technology into a completely new era of performance per amount of speaker. So loudness per amount of speaker. We also make the amps to drive all of those. So nowadays, those amps are quite extraordinary. We just launched 16-channel amps. Each channel is 1,300 watts in just a 2U chassis. They're network controlled. They have DSP integrated in them. And so to configure all of this stuff, software has been a big part of what we do for quite a while already. So this is our sound vision software, which is our acoustic modeling tool, which is a very important tool to be able to predict the performance of a sound system in a venue. And this is our network manager tool, which is used to control remotely amplifiers, because you may have up to 200 amplifiers in a venue, and you are not going to turn 200 knobs just to bump the volume a little bit. And you can see we can do EQing on there as well. Yes, so for the past 8 years, we've been working into the realm of spatial audio as well. And so we're going to talk about that today, and hopefully you will learn something interesting along the way. So Fred is going to talk mostly about the algorithms, why you would want to do this, and then I'll jump to talk a little bit about product development history, because I think there's quite a few interesting little pieces of advice maybe, or at least experience that could be interesting to a lot of us.
All right, thank you, Olivier. So I'll start by talking about where we are today. Let's say what you've been used to mostly in concerts, before building up to what we mean by immersive audio and object-based audio, and then the specific, let's say, challenge of scaling it to a large audience. So typical left-right system that you experience in concert, there's very little use of panning. Panning that you may have in your stereo recording, your left-right, your positioning, careful positioning of objects. Actually, in a concert, you end up, in practice, having a dual mono experience. A lot of it is down to the problem of coverage of those line arrays. They are basically each covering mostly part of the audience. So in the end, what you experience is a mono feed, basically, from the mixing console. And for your brain, to separate all of the different instrument sources that are coming from one mono source is difficult. So it leads to fatigue, really. But not only that, but also because this sound is coming from the nearest loudspeaker. This is a precedence effect. What you see on stage, the singer on stage, and what you hear actually also are quite separate physically. And again, your brain is pretty smart into merging those two back perceptually, but yet it's still, again, something that leads to this conflict, and this is a bit of confusion, a bit of fatigue. So this is not very natural. We've been used to it, but here at Acoustics, Elisa, this is part of the reason we wanted to go beyond. So here comes object-based mixing. So you may have, most of you have heard of it. The principle is fairly simple. It's about you take a mono audio object, you describe it with high-level metadata in terms of positioning, so the pan or azimuth, the elevation, also the distance often, and the width or extent, basically how large this sound object will sound. The good thing is this fits pretty well in the workflow of live mixing console, where already you have those different strips for your instruments. Now, how it looks like in practice, in deployment for live concert, you have your ELISA processor. So this is your spatial audio processor, and Olivier will describe a lot more about that a bit later, where all your audio objects, your streams, will go through, right? Then you have the controller, which will describe and control the sound scene, basically, the positioning, the relative positioning of all the objects relative to the mixing position in our case. So including the distance, for example. And the processor will take those metadata and will do the spatial audio algorithm to place them in space for the audience. What you have optionally on top is those controls. Then they can come also from various angles. They can come from the mixing desk. The mixing desk can include some what we call desk links, so you can straight from your console control some of those objects. So you have that tight integration, possibly. Or if you're more in a studio, you may also use our plugin, for example, so that you can straight from your regular Pro Tools or Reaper or Ableton or whatever, you can use those kind of things. So what is the benefit of the immersive system? So as I said, there was this fatigue, and here we are, we call it unmasking. So by separating physically again, the different instruments, like they are in real life, if you go to acoustic concert, then you allow your brain to process much more easily the different melodies, the different texture, the different lines, basically, of music. So you can allow a richer music. You are a bit freed from the challenge of mixing with basically dual mono. Also, what you have is you have back the audio and visual fusion. What you see and what you hear, they are all now naturally aligned. And the end result is the PA disappears. You don't feel like there is a PA anymore. It's basically it becomes much more blended with what's happening on stage. So this is a big benefit. And indeed is this rich and natural audiovisual environment, which having this like more higher resolution canvas allow you then to go beyond what you were restricted to in a live environment. But of course, there are also challenges, because many of those technologies were available for quite some years and decades in the lab. But what was possible in a studio, where basically everything is at well positioned, same distance, so you have no problem controlling space, the position of objects, their distance, their level, their frequency response, but also the timing, so the time of arrival of all the sounds is very well controlled in a studio. Now, when you start to scale up to a large audience, where there are tens of meters and the speed of sound is unfortunately not that fast, then you run into quite a bit of problem. Problem again with space. So what you placed in a studio at this 45-degree angle, how is it for the audience? Of course, it won't be the same, depending on where they are. Same for the level, the frequency response, because each speaker that will reproduce this will have a certain coverage, a certain reach, basically, a certain throw over the audience. And the time is maybe even the most tricky one, because you can't really tackle that easily. If you are close to a speaker, really at the back, then how do you feel about the mix? Will it be still the same, or will it sound quite differently for you compared to someone in the middle, somewhere on the right? So lots of really interesting and difficult challenges. And so it relates to the loudspeaker design. So how the system design, how do we design that system to mitigate a bit those problems? How do we design algorithms also to help a bit? And not only that, but we also means the mixing engineer needs to be aware of that, needs to anticipate those kind of problems. Some of them, like for example, time of arrival, might mean that some of the rhythmic elements of a mix need to remain together and not be exploded in space, like it would sound cool in a studio, not in a large arena, for example. I will briefly mention a bit those kind of loudspeaker design elements to at least, for you to have a little bit of a understanding of how we approach it. So if we take like an immersive frontal system, so we are just still adding the resolution in the frontal system. You see here the 5 full range sources at the front, at the top. So we add that resolution to, again, have that better consistency between visual and what's happening on, in the audio. And one very important and logical requirement is each of those speaker need to cover completely the audience. There needs to be a really good cross coverage of the audience. That's a requirement. Otherwise, if you pan in a certain speaker, for example, if part of the audience doesn't hear it, then it's pointless. So there are strong requirements on how you build such frontal systems so that it works, and you can be freely panning something like that. Now, when we start to add, let's say, other dimension, for example, you can extend the panorama beyond the stage, that's the extension, or you can have the surround and overhead. They all add interesting space to the canvas where you can play creatively, but also they will have their requirements in terms of coverage for the audience, and which can be even more tricky because often walls tend to be close to the audience when you are for the surround speakers in particular. So I won't go too much here in details about this how you get to design, because this is quite an advanced topic. And as Olivier was saying, we have this software called Sound Vision helping the sound designers, the sound system designers, to make sure to qualify that indeed you will have the right cross coverage, the right tightness of time of arrival for a given audience. Now, that was the system design, basically a foundation without which you cannot really do much of anything. So in terms of algorithm, at ELISA, we use an amplitude-based panning to deliver the source in a given position in space. So it's a close cousin of the VBAP that is quite well known. So it's you can think of it of the spatial version of the stereo panning. So basically amplitude panning, but in space. And it's quite simple. It's basically you identify the pair or the triplet of speakers that are the closest to the direction you are interested in. And from there, you will compute the gains, the right balance of gains, basically to deliver the right phantom source for this pair or triplet. So very, in a way, quite straightforward, but it delivers a very high, let's say, quality, and potentially the highest quality when really you snap it to a speaker to really deliver to the audience. The other part of the key component to the spatial audio is the room engine. So the room engine is where all your sound objects will belong to. They are placed in this virtual space, which help a blend to help the glue. And also, it can be used as a complement to the natural acoustic of the space, because we are not in a studio anymore, where it's treated, can be very dry. In a space, there will always be some level of natural acoustics. Might be good, might be bad, but which is part of the reason where we had also to design a room engine that is highly customizable, and you can adjust depending on what's available on there. The room engine is also important in the perception of distance, because you have those objects, and this perception of distance, a lot is related to this ratio of direct to reverberant sound. That's part of it, also the early reflection. So therefore, we have like those automatic, basically, control of those different ratio to mimic, to give that impression of distance, basically. So, but this is like a room engine, and now I was talking about the problem of scaling, and room engine has its own challenges, because you're dealing with space and long time of travel, and that means we need to, for example, guarantee, and that's what we call precedent safeguard. We need to guarantee that the source that you place in space, the direct sound will arrive before the room engine, and that requires care, because it's easy to get the late reverberation, for example, arrive before. That would definitely be bad for the intelligibility, the clarity of the message. So therefore, we have baked in, basically, inside our room engine, some of those features to allow you to scale something that you've listened to in a studio, and that will still deliver it in the best way possible over a large audience. We have a lot of interesting, nice control from this room engine, but I won't go too much into details. I was just giving here a bit of context of what spatial audio, immersive audio is, and for Olivier to continue. But before that, just an example to illustrate a bit how, in some ways, let's say ELISA and immersive audio, spatial audio for live, has now reached a high level of acceptance already around the world. This is an example of this venue in Las Vegas, Resort World Grand Theater, where a lot of the top artists have been already using this system. The first one, Carrie Underwood, was last year in December. But there are many. Also in London, we have the ABBA Arena, where the ABBA Voyage show is running, is also using our technology, the ELISA, and yeah, so very exciting. So now a transition to Olivier, back to explain a bit how we did it.
Cool, thank you, Fred. So let's talk a little bit about code. So I want to give you a little bit of project history first, because I think it's really interesting to see what we've been able to achieve in those 8 years, to go from an ID, no code, to a product that's today used for big shows, that is production ready, that is stable. And some challenges along the way. We're mostly going to talk about performance, because we do a highly multi-channel system. So our processing engine can do 128 inputs into 128 outputs. And so for anyone who has tried to optimize a plugin or a DAW or anything like that, you will know that it's always a challenge to cram as much DSP in the processing power you have available. So let's start with the project history. So we started in 2014. And this started as a collection of Max patches. So Max is being this graphical audio programming environment from Cycling 74. And our platform that we were selling as a product at the time, or actually we weren't selling it, we were giving it to close friends to try it out. It was running on an off-the-shelf industrial rack mount PC, so just normal Intel CPU, like nothing special here. And it was running on Windows 8 embedded. And the reason for that is the prototyping environment was also the product. So Fred at the time, who was the first employee at ELISA, was able to prototype on his Windows laptop with Max, try some things. It's very easy to iterate, change things. And then once you're happy with it, Max is actually great for that. You can very easily export a runtime that doesn't require the entire Max environment. And ship it in the product, and that's your product. But obviously, at some point, you start hitting some bottlenecks. So Max is great, and we were really surprised by the amount of performance we could get out of it, but at some point, you need to have tighter control. So in 2018, we started rewriting the entire audio engine in C++, and we released that in 2020. So this was an important phase, because that took about 24 months to do that. And during this entire time frame, we weren't able to add new features. So the moment where you decide to do this transition from whatever your first prototyping environment is to something that's a bit more future-proof, a bit more, which will give you more performance, is quite critical. And there are histories in the industries of Microsoft, I think, trying to rewrite Word from the Office suite from scratch because they didn't like their legacy code base and they couldn't ship any new features for 3 years. And in the end, it turned out that the rewrite was more buggy than the old code base, which had been fixed for 10 or 15 years, and they ended up scrapping it. So this is a risky endeavor, but it can be done. So it was still running on the same hardware platform, still Windows 8 embedded, so still fairly easy to develop. You can run it on your machine, and then you port it to the target platform. No cross-compiling, no remote debugging, none of that. Then we changed the operating system. We went from Windows to Linux RT. I'm going to talk a little bit more about Linux later on, why it's so great. But basically, Windows embedded first there's a cost associated to it because you have to pay a license for every deployment. That makes reflashing in the field, if your customers have issues, problematic because you need to give them a Windows license key, or there's automatic activation systems that don't work if you don't have internet, all that kind of stuff. And then later in the year, we introduced our custom hardware. So something that looks a bit more polished with a proper chassis, with the same industrial design as our other products. It has rugged connectors on the back that are suited for touring use. It has redundant power supplies. It has, well, you can't really see it on that picture, but it has nice little LEDs on the front panel so that you can see if there's an error, a problem with the system quickly. But it's still a PC-based platform, still Intel chip, so nothing special here. And I want to expand a little bit on that, actually, because at L Acoustics, in our amps, we have FPGAs, we have DSP chips, and there was this question at some point of whether we wanted to stay on x86, 64-bit, off-the-shelf, normal Intel CPU, or to move to a DSP chip or FPGA. And so there are things that are great with those FPGA or DSP-based platforms. For example, you get a lot better performance per watt, so your product can be a lot sleeker. We could probably make this box 1U, maybe even like half U if it was on the FPGA. In our amps, the DSP card is a PCB like this big with a tiny heatsink on it. So it would be quite sexy. It would be interesting. But the problem is the development times are way longer. It's way harder to debug FPGA or DSP code, and the talent pool is much smaller. So who can do FPGA development in the audience? Yeah, no one. Who can do C++? Yeah. So, I mean, I guess I'm at a C++ developer conference, so that explains that there may be a bias in this poll, but you get the idea. So we decided to stay on this because for the ease of development, for the ability to still iterate quite fast with C++, not as fast as with Max, but still quite fast. And actually, there are a lot of competitor products from brands that have similar positioning on the market, and they all do the same thing. So everybody came to the same conclusion. The other bonus is we can take our C++ code and we can also ship it as a piece of software that you run on your laptop. And then we can sell software instead of selling hardware, which is a new business opportunity for Acoustics. And there's a QR code at the end. You can download it if you want to try. So let's talk a little bit more about Linux, why it's so great. As I said, first, it's free, so that's always good. We're going to talk a little bit about the RT patch to make it a real-time OS. And I'm sure all of you have been to one of those talks that tell you don't use mutexes, don't do memory allocation, don't do any of those things. On a real-time OS, a lot of those limitations now are lifted. You can do that because your OS works for you, with you. It's super customizable. You can take an off-the-shelf distribution. In our case, we use Debian, and then you can strip it down as much as you want. It's super easy to add more stuff to it. And more importantly, it's understandable. So if you don't know what your operating system is doing, or rather, typically one of the components that comes with it, for example, I don't know, an example would be the IP addressing, like the DHCP client on Linux. We were having issues with some DHCP timeouts. We were wondering what was happening. What was the timeout? You can just dig into the source code and find the function that does that, and you will see, okay, first it tries. Then if it fails, it will wait 2 seconds, try again, then wait 4 seconds, then try again. If you wanted to troubleshoot an issue like that with Windows embedded, you would either have to look for external signs. Let's say Wireshark it and see what it does. But then you'll be wondering, does it always do that? Is my setup different? Could it be doing something different in a different case? Or you need to phone someone at Microsoft. And I mean, no offense, but we were a small customer. It's always hard to get good, quick support as a small customer. I'm sure they can provide the information, but that takes time. And when you're a C++ developer, it's not that hard to dig into the Linux source code and figure things out. So it's understandable. Just read the source code. That means you can self-support yourself. If you don't understand something, you can read it. If you find a bug, you can fix it yourself. The one thing that's a bit hard is drivers. So in our case, we need to talk to a multi-channel sound card. And drivers can be a bit hard because manufacturers don't usually release Linux drivers. Most of the Linux drivers are reverse engineered by the community. So that's why it can be a bit hit and miss. There are specialized companies that can help you with that. If you have a good relationship with the manufacturer, you can ask them to maybe help you with that. But that's where you need to be a bit careful. So now let's talk a little bit more about how we were able to swap all those components one by one. So the audio engine, the operating system, and the hardware, while still keeping faith in our product and making sure we weren't breaking anything along the way. So I think you all know the answer to this, and this is automated testing. So at LL Acoustics, because we make products for live, where a bug is not just an audio glitch for someone using a DAW in their studio, it's for an entire audience, maybe 10,000 people, 20,000 people. We have a very strong culture of reliability. And we actually are lucky to have a dedicated firmware testing team. And what's great with having a dedicated team is it's their job to find the problems. If it's your code, you're going to do the minimum to say, yeah, it's tested. And you always have a bias because you wrote the code, so you know what you're not going to think about all the same edge cases that a different person will do. So I will always say the person that writes the test shouldn't be the person that has written the code. That's definitely the way to go. And also, when we're bored, we're thinking about new features. If we have free time, when they're bored, they just add more tests and they try new things, new ways of breaking it. So if you can allow it, definitely having dedicated testing staff has been proven greatly beneficial, and they keep finding bugs that we would have never found if they weren't there. So this is a little picture of the testing rack. What's important is that it's fully black box testing. So they have this device called an audio precision, which is an audio analyzer that's remote controllable. It's typical lab testing equipment for this kind of stuff. Generates audio, pipes it through the device, listens to the output, and then you analyze it. So maybe you're measuring a delay, a frequency response, a gain, whatever. Which means that if anything goes wrong, you'll see it, right? So if the sound card driver is bad, you'll see it. If the device overheats and the CPU starts to throttle down and you start getting performance issues because of that, you'll see it. And they can also test all the kind of stuff that we wouldn't really test. For example, does it keep its settings when you pull the power out and you put it back in? So they can remotely remove the power on the device, put it back. Does it start up again correctly also when you put back the power? And then they generate nice little reports like this. They're great at explaining what the test does. And for example, here we have a frequency response test for our binaural engine. And the frequency response should fit, so for the left channel between those two lines, for the right channels between the other two lines, and you can see it's flat, so something is wrong there. And you get the pretty graph. You can, maybe if you're a developer, you can immediately tell, oh yeah, maybe I forgot to call the function that actually sets the coefficients of that filter, or whatever. So that's great. But as a developer, this is as far as it could be from test-driven development. It doesn't really help you write your audio algorithms and make sure that what you're doing is what you should be doing. So I'm not going to talk about unit tests. Write unit tests. Everybody should be writing unit tests. They're great to test a little bit of functionality like a filter, but ultimately the algorithms that the Fred's team specify are a collection of a bunch of DSP blocks, a bunch of filters, gain stages that all need to work together. And at some point, you need to just test the whole thing. And we came up with, I think, quite elegant way of doing that, and that's easy to replicate. So if you're using Juice, so that's first if, so we're using Juice, you can very easily implement a custom Juice audio I/O device type and Juice audio I/O device to basically do a mock for the sound card driver. And then we have this basically virtual audio device that will hook into the Juice framework even before it reaches our code. So our entire code, our entire audio code is tested from start to finish. So if this works, there's a high chance that it will work with a real sound card, unless there's a bug somewhere in Juice, which obviously could be the case. So we send an OSC message to trigger a recording. So what this will do is it will generate some signal. So often we measure impulse responses, and it will save the output to a WAV file. And we do this within Python. Python is great to write integration tests because you can tweak your code, rerun it, unlike C++. I mean, writing tests in C++ is a pain. Like your test fails, you tweak one thing, you make the margin a little bit bigger, you wait 2 minutes for it to recompile, rerun. In Python, you can be a lot quicker. So Fred has developed a bunch of toolboxes to do audio processing, check frequency responses, measure delays, all that kind of stuff. And then so in Python, we read that multi-channel WAV file. We process the output, and then we get a test pass-fail. And then we can run this on our CI. And more importantly, you can run this on your machine as a developer while you're tweaking things. You can change a DSP parameter, change a gain, and rerun the test live without having to recompile, relaunch the program. So something to try if you're interested. It's maybe 200 lines of code to do this custom audio I/O device type audio I/O device. So it's not very hard. So now that we have DSP code that does the right thing, how do we make sure it's fast enough? And that's actually the biggest problem for us. So I assume most of you are familiar with the concept of audio callback and the audio callback deadline. I don't see too many people seem confused, so let's say that. So for us, that's the main thing we want to look at is our code fast enough? And also, if it's fast enough, are we flying too close to the sun, right? Because you never know. Maybe one day will be just a tiny bit slower, and that would bring you over the edge. You get a glitch. For us, it's completely unacceptable. So what we've done is we've expanded on the thing that's actually already in Juice. So in Juice, there's already an audio load meter, which is not a CPU load meter. It's time-based. It's measuring the time that the audio callback needs to execute. And you always want this to be shorter than the length of your audio buffer. And so we've added the same thing, but it's graphing. So we have a little line, and we can also measure different parts of our audio graph independently. So we can say, okay, is it the reverb that's taking more time? Is it the panning? Is it some other kind of post-processing? And we can see the line live, and the white line here. So in that example, we are running at a quite high block size. That's our deadline. So we always want to be below that white line. And you can see it's quite spiky. So that's running on Windows. We're doing a bunch of maybe not super real-time safe stuff. So maybe that's why. What's great with it having live like that is you can you can measure the impact of DSP parameters live. So for example, maybe you have some DSP blocks that will take a longer time to execute depending on parameters. So an example for us would be our reverb. So I'm not going to dive too much into the details, but basically the longer, it's not a convolution reverb, but if it were a convolution reverb, if you have a short reverb tail, you have less non-zero coefficients in your convolution than if it was long. So it's going to take more CPU if you have a long impulse response, whether you have a short impulse response. And so you can use this, you move your slider, you see, oh, if I'm at half a second decay time, it's fine, but if I'm at 5 seconds decay time, now it blows up. So that's one of the reasons why this live profiler is good. The other thing is when we're starting playing with real-time OS, where we start tweaking thread priorities, thread affinities to pin certain threads on certain CPU cores, this can all be done via usually the command line interface. So you can do this live while your program is running. And then you can see the impact of the tuning you're doing live, which is great. Then you want to validate that what you've done is good. So we have a way of logging the output of this thing to a file, and then we run long soak tests on our CI nightly. So I think they're 4 hours. So we run 4 hours of audio, and we measure the time it took to execute every callback for 4 hours. And that's a lot of data, so we can't keep all of it. So we aggregate it, and we keep the max and the average. And the only thing we really care about is the max. And this is an example on how it looks like so it's plotted. So it's on the x-axis, you have each audio callbacks or a group of audio callbacks. And on the y-axis, it's the time it took to execute. And we still have our deadline there. And here you can see, so that was running on Windows 8. You see all those spikes, and all those spikes are really bad because on average, that's where our average is. So on average, we need half the time we have available. But quite often, we're closer to 75% of the time we have available. And that means we can't really cram a lot more DSP into our product, because at some point, one of those little spikes is going to go over the line, and we're going to get a glitch, and we won't be happy. So that tells you if something is wrong with your thread scheduler. Maybe you have some non-real-time safe cores that are causing those spikes. Then it can be quite hard to troubleshoot, but at least you know where you stand. This is an example of a pretty bad bug. So the deadline is here. It's all fine and good, and at some point, for whatever reason, the execution time skyrockets. And that's something that you may not see. Again, like you see, it takes like 6 seconds for this to happen. Will you see that on your machine? I'm not sure. And if you execute it on your machine, you'll be, oh yeah, that's my debugger. That's like slowing my process down or whatever. Or maybe it's Chrome update in the background. You're likely to dismiss it. So this is running on the target hardware with the target operating system. So if this happens, then it could happen in the field. In that case, it was a nasty case of denormals number not being disabled on some background threads. So make sure your denormals are disabled if you have recursive filters, because otherwise you'll always, this will happen to you. And it's per thread. So now let's talk about the techniques that we can use to flatten those spikes and then raise the average to get more performance. So on Windows, there are actually a few things you can play with. The Windows, we've seen that generally you will create one thread per core you have available. And if you load balance your work between those threads, you're doing all you can do to make it as good as possible. But sometimes your thread scheduler of your OS will be a bit dumb and will say, oh, I have 8 cores, there's 8 threads. I'm going to put threads 1 and 2 on the first core and put nothing on the last core. And that's going to tank your performance. And you can really easily fix that by using thread affinity, which is pinning certain threads to certain cores. This is available in Windows. So obviously, you can only do that if you're in full control of the operating system. You can't do that for a consumer product that runs on a consumer machine. But it's available in Windows. And then Windows has also real-time thread priorities. But these are just hints to the scheduler. And no one really knows what it does, what are the heuristics of the scheduler. So that's the best you can do. On Linux, we have all of the above, plus the real-time patch. So I won't have time to dive too much into the details. Maybe I'll do another talk next year about that if some of you are interested. But basically, the RT patch makes the Linux kernel a lot more predictable. That's the idea. So it actually reduces the performance a bit, the average performance, but it makes it a lot more predictable. So if you lock a mutex and you have a real-time priority, you know you will get it if you don't have it. And then we have thread real-time priority, which is kind of the same thing as what's above. So again, we really love Linux for that because it gives us a lot of control. We can really dig in. And it's also super debuggable. So this is using the perf and trace commands tools on Linux plus a bit of custom preprocessing to make the data look a bit nicer. So on this graph, each line represents a CPU core. So we have a 6-core hyper-threaded processor, so we have 12 logical cores. And each one of those colored blocks is a thread executing. This is for one audio callback, so this takes about 1 millisecond. So the data you're seeing is about 1 millisecond worth of data. And we can see here, oh, that thread executed for 3 microseconds longer than this other thread, so we're losing a bit of performance because we have to wait for them to finish. So you can really dig into what the scheduler is doing. That can help you inform decisions about how you want to balance the load between your threads. And if something goes wrong, you will see it and you will be able to debug it. So one of the awesome things on Linux. And if we look at the results, this is the same graph as before. So the only thing that's important in this graph is the red line, which is the maximum audio callback time. And you can see that we've gotten rid of all the spikes. And this is amazing because all that margin that we have is DSP power we can tap into in the future if we want to. And that's it for Linux. And if maybe next year there will be another talk just on that because it's easy to fill 40 minutes just discussing about this kind of stuff. And Fred will now talk to you about the future of immersive audio. So very briefly, it was just to at least finish also on a kind of more like an open note on saying that there's still a lot that we need to tackle in this field of immersive audio. From the studio workflow, where there's still a lot of pain points really along how you create really immersive content, and we are working heavily on that. The pre-production topic is also a very important one. I mentioned that the constraints of playing live, playing to large space and so on can be tricky, and that's important to give the right tools, the right pre-visualization, pre-listening to the creator, so that they will understand what it means to be in a different part of the audience and so on. So those are really important, also part of what we need to do. And then distribution, it's also one. I mean, there was yesterday talk about ADM, but there's also how do we standardize, how do you make sure that, let's say, the immersive audio can be something that scales across the industry and is easily shared. People can work together, and this is also an important element of what we do. Maybe before the Q&A, we have some open positions. We are sponsors of the ADC as well, so you can come talk to us at our booth if you're interested. And all the products we've discussed, as I said, they're available on desktop platforms. So the binaural version is completely free, and the multi-channel output version, there's a free trial. So scan this if you're interested, or you can come see it at our booth. For now, it's Mac only, but the Windows version is actually coming out next week. Thank you.